If you've ever stood near an airport runway watching planes land, you've probably witnessed something that looks completely insane. A massive aircraft weighing somewhere around 300,000 to 400,000 pounds drops out of the sky at speeds that would get you arrested on any highway in America. And then, boom! The wheels slam into concrete, traveling at roughly 170 miles per hour. The tires aren't spinning before they hit. They go from absolutely motionless to matching the aircraft's speed in literally a heartbeat. You see that distinctive puff of smoke, hear the screech, and somehow those tires just don't explode into a million pieces. Which seems like it should happen, right? I mean, if you tried this with your car, dropping it onto pavement at even 60 miles per hour with locked wheels, you'd be shopping for new tires, new suspension, and probably a new car. So, what's going on here? Here's what makes this even stranger. A typical wide-body aircraft tire hits the runway with enough force to leave skid marks that are visible for days, maybe weeks, depending on traffic. The rubber temperature spikes instantly to over 400 degrees Fahrenheit from the friction alone. The tire has to accelerate rotationally from 0 to something like 1,200 revolutions per minute in about half a second, while supporting tens of thousands of pounds of weight on each wheel. And this happens on every single landing, sometimes multiple times a day for the same set of tires. Commercial aircraft tires are rated for around 200 to 300 landings before they need retreading, which sounds like a lot until you realize a busy short-haul aircraft might make 6 or 7 takeoffs and landings in a single day. The physics involved here are genuinely wild, and there's way more engineering packed into these hunks of rubber than most people realize. The story of how we got to modern aircraft tires actually starts way back in the early days of aviation. And honestly, it's kind of a miracle anyone survived those first flights. The Wright brothers' first successful flight in 1903 didn't even have wheels. The Wright Flyer launched off a wooden rail system and landed on skids, basically belly flopping onto the sand at Kitty Hawk. Early aircraft designers weren't exactly worried about tire technology because, well, they were still trying to figure out how to stay in the air for more than a few minutes without crashing. When wheels did start appearing on aircraft around 1910, they were basically bicycle tires or modified automobile tires. These things were laughably inadequate for the job. They'd blow out constantly, couldn't handle rough fields, and forget about landing on anything harder than grass without risking a catastrophic failure. The real breakthrough came during World War I, when aircraft development accelerated like crazy out of military necessity. Suddenly, planes were getting heavier, faster, and more complex, and the tires had to keep up or pilots would die. The French company Michelin, which had been making bicycle and car tires since the 1890s, started experimenting with aviation-specific designs around 1912. They developed tires with reinforced sidewalls and different rubber compounds that could handle higher speeds and heavier loads. But even these improved designs were primitive by modern standards. Aircraft were still relatively light. A Sopwith Camel from 1917 weighed only about 1,400 pounds fully loaded. So tire failures, while common, weren't usually catastrophic. The plane would just skid to a halt on its belly. The pilot would climb out cursing and mechanics would jack it up and slap on a new tire. Everything changed after World War II when commercial aviation exploded and aircraft got dramatically larger and faster. The Douglas DC-6, introduced in 1947, weighed over 48,000 pounds empty and could cruise at 315 miles per hour. Suddenly, tire manufacturers were dealing with loads and speeds they'd never encountered before, and the old designs simply couldn't cut it anymore. There were incidents throughout the late 1940s and early 1950s where tires would fail on landing, sometimes causing the aircraft to veer off the runway or even flip over. In 1951, a United Airlines DC-6 had a tire blowout during takeoff at San Francisco International Airport, which led to the plane crashing and burning, killing everyone on board. That was a wake-up call for the entire industry. Engineers realized They needed to completely rethink aircraft tire design from the ground up because the consequences of failure were now measured in dozens of lives lost. So, what did they figure out? The answer lies in a combination of material science, structural engineering, and some honestly brilliant compromises. Modern aircraft tires aren't just scaled-up car tires, they're fundamentally different machines designed to handle forces that would annihilate anything you'd find in an automotive shop. Start with the rubber compound itself. Aircraft tires use a specialized blend of natural and synthetic rubber that's engineered to withstand enormous temperature swings. When a plane is cruising at 35,000 feet, the tires are exposed to outside air temperatures that can drop to minus 60 degrees Fahrenheit or colder. The rubber has to stay flexible at those temperatures without cracking or becoming brittle. Then, minutes later during landing, that same rubber needs to survive being instantly heated to over 400 degrees from friction without melting, degrading, or catching fire. Try doing that with a normal tire and you'll end up with either a frozen brick or a puddle of goo. The internal structure is where things get really interesting. Aircraft tires are built with multiple layers of reinforced fabric cords, usually made from nylon or Kevlar, arranged in a crisscross pattern called a bias ply construction. Some newer tires use radial construction similar to car tires, but bias ply is still dominant in aviation because it provides better resistance to the kind of brutal impacts that happen during landing. These fabric layers are embedded in the rubber and run at angles to each other, creating a mesh that distributes stress across the entire tire. When the tire hits the runway, instead of all that force concentrating in one spot and causing a blowout, it spreads out through this internal web. It's like the difference between punching a single sheet of paper versus punching through a whole ream. The energy gets absorbed and distributed rather than punching straight through. Then there's the inflation pressure, which is absolutely bonkers compared to car tires. Your average car tire is inflated to around 32 to 35 pounds per square inch, maybe 40 if you're driving a heavy truck. Aircraft tires? Try 200 psi for smaller planes and up to 250 psi or even higher for large commercial jets. Some military aircraft use tires inflated to over 300 psi. This extreme pressure serves multiple purposes. High pressure means the tire deforms less under load, which reduces the rolling resistance and helps with fuel efficiency, a huge deal when you're burning thousands of gallons of jet fuel per flight. It also means the tire can support more weight relative to its size, allowing engineers to keep the landing gear compact rather than requiring enormous wheels that would need massive storage bays. But here's the catch. High pressure also means there's tremendous energy stored in that tire, which is why ground crews treat them with serious respect. A tire failure at 200 psi can kill someone standing nearby, and there have been fatal accidents involving aircraft tire explosions during maintenance. The tread pattern on aircraft tires is another crucial element that's easy to overlook. Unlike car tires, with their complex arrangements of grooves and sipes designed for all-weather traction, aircraft tires have relatively simple tread patterns with straight circumferential grooves. This is deliberate. The primary job of aircraft tire tread isn't to provide grip in the rain or snow, though they do need to channel water away to prevent hydroplaning. It's to handle the enormous heat generated during landing and to wear evenly over hundreds of landing cycles. Those straight grooves help dissipate heat by allowing air to flow around the tire more efficiently as it spins up during landing. They also make it easier to inspect tire wear and determine when retreading is necessary. Some aircraft tires, especially those on smaller planes that operate from grass or gravel runways, have more aggressive tread patterns, but even these are nowhere near as complex as automotive tires because the requirements are completely different. Now, let's talk about what actually happens in those first few seconds when a plane touches down, because this is where the engineering really shines. The moment the tire makes contact with the runway, several things happen almost simultaneously. The tire instantly deforms as it absorbs the impact. The bottom of the tire flattens out against the runway in what's called the contact patch, which for a large aircraft might be only about the size of a standard sheet of printer paper per tire, despite supporting tens of thousands of pounds. At the exact same moment, friction between the stationary tire and the moving runway creates incredible heat and begins accelerating the tire rotationally. The tire doesn't just start spinning smoothly like a car tire would. There's a brief moment of skidding where the tire is actually sliding along the runway surface while gradually catching up to the aircraft's ground speed. This is where that smoke comes from. It's literally vaporized rubber and heated moisture being thrown off the tire. The acceleration forces involved are staggering. A Boeing 777 might touch down at around 160 miles per hour, which translates to the outer surface of the tire needing to accelerate from 0 to about 235 feet per second in less than a second. The rotational inertia of the tire assembly, the wheel, the tire, the brake system, has to be overcome essentially instantaneously by friction alone. This generates enough heat to raise the temperature of the contact patch by several hundred degrees in a fraction of a second. The tire survives this because of that specialized rubber compound we talked about earlier, which is designed to handle rapid heating without breaking down. But there's a limit. If a pilot lands particularly hard, or if the tire is already worn or damaged, or if conditions are just wrong, the tire can fail. Usually, this manifests as chunks of tread separating from the tire body, but catastrophic blowouts do happen. And when they do on a large aircraft, it's genuinely dangerous. Interestingly enough, one of the most critical factors in preventing tire explosions during landing isn't even in the tire itself, it's in the landing technique. Pilots are trained to touch down as smoothly as possible, but they also need to balance that with getting the wheels on the ground firmly enough that the weight on wheels sensors trigger immediately. These sensors activate various systems, including the ground spoilers, which help slow the aircraft, and the auto brake system. If the landing is too gentle and the sensors don't trigger right away, the plane might actually bounce slightly or float down the runway, which wastes precious stopping distance and can lead to a harder second touchdown. So there's this delicate balance, firm enough to activate the systems and get the tires spinning up properly, but not so hard that you risk damaging the tires or the landing gear. Experienced pilots make this look effortless, but it's the result of thousands of hours of training and muscle memory. The braking system works in tandem with the tires to slow the aircraft after touchdown, and this is another area where things get complex fast. Large commercial aircraft use carbon composite brake discs that can absorb and dissipate enormous amounts of energy. During a typical landing, the brakes might heat up to over 1,000 degrees Fahrenheit, glowing dull red in the darkness if you're landing at night. The heat radiates outward, and some of it conducts into the tire itself. Through the wheel assembly, the tire has to survive this additional heat load on top of everything else it's dealing with. This is why you'll sometimes see fire trucks following a plane that's just landed after an aborted takeoff or emergency landing. They're standing by in case the brakes or tires catch fire from the accumulated heat. It doesn't happen often, but when it does, the results can be spectacular and dangerous. There's also the matter of tire maintenance and inspection, which is way more involved than most people realize. After every flight, ground crews conduct a walk-around inspection that includes checking tire pressure and visually inspecting for cuts, bulges, or excessive wear. Aircraft tires have wear indicators built into the tread, similar to car tires but more sophisticated, that tell maintenance crews when the tire needs to be replaced or retreaded. Retreading is a major part of aircraft tire economics. A brand new tire for a Boeing 747 can cost several $100s, but it can be retreaded multiple times over its life cycle. The process involves stripping off the old tread, inspecting the tire carcass for damage, and vulcanizing on a new tread layer. A tire might go through 3 or 4 retreading cycles before the carcass itself is too worn or damaged to continue using. This is economically crucial for airlines, which are already operating on thin margins and can't afford to be replacing tires constantly. One of the more sobering aspects of aircraft tire design is what happens when things go wrong. Tire failures during takeoff are particularly dangerous because the aircraft is at high speed, heavily loaded with fuel, and hasn't reached a safe altitude yet. There have been cases where a blown tire during takeoff threw debris into the engine or punctured fuel tanks, leading to catastrophic accidents. The crash of Air France Concorde Flight 4590 in Paris in July 2000 was triggered by a piece of metal on the runway that burst one of the Concorde's tires. The debris from the tire punctured a fuel tank in the wing, causing a massive fire that brought down the aircraft and killed everyone aboard, along with people on the ground. That accident led to major changes in how aircraft tires are certified and how runways are inspected for debris. Modern tires are now tested to withstand impacts from foreign objects and to fail in a more controlled manner if they do rupture, rather than disintegrating completely and sending shrapnel everywhere. The future of aircraft tire technology is heading in some interesting directions. Manufacturers are experimenting with new materials, including advanced composites and even airless tire designs that eliminate the risk of blowouts entirely. Michelin has developed a prototype airless aircraft tire using a honeycomb structure made from resin-impregnated fibers that can support the same loads as conventional tires without needing inflation. The advantages are obvious: no blowouts, no pressure maintenance, potentially longer service life. But there are challenges too. The airless design changes how the tire absorbs impacts and dissipates heat, and it's heavier than conventional tires, which matters a lot in aviation where every pound counts. Whether these designs will eventually replace traditional aircraft tires remains to be seen, but the research is ongoing and serious. So when you watch that next aircraft touch down and see those tires smoking as they spin up to speed, you're witnessing the result of over a century of engineering evolution. Those tires represent countless hours of research, testing, and refinement. They're dealing with forces and conditions that seem like they should be impossible to survive, yet they do it reliably hundreds of times over their service life. The fact that tire-related accidents are now relatively rare in commercial aviation is a testament to how well this technology works. Engineers figured out how to build a tire that can sit in sub-zero temperatures at altitude, then get slammed into concrete at highway speeds, spin up to over 1,000 revolutions per minute in less than a second, withstand 400-degree temperatures, support hundreds of thousands of pounds, and then do it all over again on the next flight. That's not just good engineering. That's borderline miraculous when you actually think about the physics involved. And yet most passengers never give those tires a second thought until something goes wrong, which is exactly how it should be.